Hello again, and welcome to another episode of Quantum on the Treadmill. Like always, these are questions I ask AI as I try to learn the mysteries of quantum. I hope you enjoy this episode. Thanks again. I'm John Willis, also known as Bocciagalupe. Before we dive into quantum mechanics, let's remember what an atom actually is. If you already know the basic structure of an atom, feel free to skip this chapter. You probably haven't forgotten the difference between a proton and an electron, but if you're anything like me, high school chemistry happened a long time ago. Somewhere along the way, I remembered that atoms had electrons flying around them, or at least I thought they were flying around them, but I couldn't have confidently explained the difference between a proton, a neutron, or why changing one particle creates a completely different element before we can understand why quantum mechanics changed physics forever. It helps to understand what physicists were actually trying to explain in the first place. And so consider this a refresher for those of us who didn't pay enough attention in science class. The atom, nature's basic building block, everything you can touch, your body, your coffee cup, the air you breathe, the earth beneath your feet, and even the stars is made of atoms. Atoms are unimaginably small. Millions of them could fit across the width of a human hair, yet every piece of ordinary matter in the universe is built from these tiny structures. And you can think of an atom as having two main parts: the dense center, called the nucleus, a cloud of electrons surrounding it. Early scientists imagined the atom as a miniature solar system with electrons orbiting the nucleus like planets orbiting the sun. We now know that's not quite right, but it's a useful place to start. Inside every atom are three fundamental particles: protons, the atom's identity. Protons live inside the nucleus. They carry a positive electrical charge, and they are relatively heavy compared to electrons. Most importantly, the number of protons determines what element an atom is. For example, one proton equals hydrogen, two protons equals helium, six protons equals carbon, eight protons equals oxygen, 26 protons equals iron, 79 protons equals gold. This is one of the simplest but most important ideas in chemistry. If you somehow added one proton to a carbon atom, it would no longer be carbon. It would instantly become nitrogen. The proton is the atom's identity card. Neutrons, the stabilizers. Neutrons also live in the nucleus. Unlike protons, they carry no electrical charge. They weigh about the same as protons and act as stabilizers that help hold the nucleus together. Interestingly, changing the number of neutrons does not change the element. Carbon always has six protons, but it might have six neutrons yields carbon 12. Seven neutrons yields carbon 13. Eight neutrons yields carbon 14. And these different versions are called isotopes. Carbon 14 is radioactive, which makes it incredibly useful for dating ancient artifacts and fossils. Electrons, the real workers. Electrons exist outside the nucleus. They carry a negative electrical charge, and they're astonishingly light, about 1,836 the mass of a proton. Although they contribute very little to an atom's weight, they determine almost everything about how matter behaves. Chemistry is really the story of electrons. Whenever atoms bond together, exchange energy, conduct electricity, emit light, or react with one another, it is their electrons doing the work. Hydrogen and oxygen don't become water because their nuclei touch. Their electrons rearrange themselves into a lower energy configuration, producing one of the most important molecules in the universe. Why doesn't the atom fly apart? Positive and negative charges attract each other, and the positively charged nucleus constantly pulls on the negatively charged electrons. And the natural question is, why don't the electrons simply fall into the nucleus? That question turned out to be one of the greatest mysteries in physics, and the answer eventually required an entirely new way of thinking about nature: quantum mechanics. We'll get there soon. Neutral atoms and ions. Most atoms contain the same number of protons and electrons. An oxygen atom, for example, has eight protons, eight electrons. The positive and negative charges cancel each other, making the atom electrically neutral. But atoms sometimes gain or lose electrons. When that happens, they become ions. For example, sodium normally has 11 electrons, lose one electron, and it now has 11 positive charges, but only 10 negative ones. It becomes a positively charged sodium ion. Chlorine often gains an electron, becoming negatively charged. Those opposite charges attract one another, producing ordinary table salt. The periodic table is simpler than it looks. The periodic table can seem intimidating, but at its core, it's simply a list of atoms arranged by one number, the number of protons. Hydrogen has one, helium has two, carbon has six, iron has 26, gold has 79. Every square on the periodic table represents a different number of protons. That's it. Everything else flows from that. Where's the mass? Almost all of an atom's mass is concentrated inside the nucleus. The protons and neutrons account for nearly all its weight. And electrons are so light that they contribute almost nothing to the total mass. An oxygen atom contains 8 protons, 8 neutrons, 8 electrons. Nearly all of its weight comes from the 16 particles inside its nucleus. Is an atom mostly empty space? Uh, Surprisingly, yes. If the nucleus were the size of a marble sitting at midfield in a football stadium, the electrons would occupy a fuzzy cloud extending almost to the upper seats. Everything in between would be empty space. Yet when you place your hand on a table, it feels solid. And that's because the electrons in your hand repel the electrons in the table. And what we experience as solid is really the electromagnetic force preventing atoms from passing through one another. And the bridge to quantum mechanics. Everything we've discussed so far is the classical picture of the atom. But by the early 20th century, physicists discovered that this picture couldn't explain what experiments were showing. Electrons didn't behave like tiny planets. Light didn't always behave like a wave. Energy appeared in a discrete packets instead of flowing continuously. Those puzzles led directly to one of the greatest intellectual revolutions in history. Max Planck introduced the idea that energy comes in tiny packets called quanta. Albert Einstein argued that light itself behaves as particles we now call photons. Niels Bohr proposed that electrons can occupy only specific energy levels. Louis de Broglie suggested that electrons themselves behave like waves. Erwin Schrödinger replaced simple orbits with mathematical wave functions. Werner Heisenberg showed that there are fundamental limits to simultaneously knowing an electron's position and momentum. The comfortable little solar system model of the atom gave way to something far stranger and far more accurate. What to remember? If you remember only a handful of ideas before we begin our journey into quantum mechanics, remember these. Protons determine the element, neutrons determine the isotope and stabilize the nucleus, electrons determine chemistry, electricity, and nearly all of the atom's observable behavior. Almost all of an atom's mass is in its nucleus. Most of an atom's volume is empty space. Understanding why electrons behave the way they do became the central question that launched the quantum revolution. As we'll soon discover, explaining the behavior of one tiny electron forced scientists to completely rethink reality itself.